to everybody, welcome. Thank you so much for coming. This is actually our second year doing Astronomy on Tap, and we're very glad that there's still people showing up to have cool science and drink beer. So cheers for that. Cheers, everybody. Woohoo. Yeah, by the way, if you like origami and stars, I have like origami papers, so I can spread around, and some people know how to make it, so you can just follow a YouTube tutorial if you don't know, or if not, you can ask her help. Yeah.
All right.
Yeah, no worries, no worries. So, our first speaker is called Michele Citran.
Citran.
Please, an applause to him.
Scusate.
Yeah. And, okay. Besides falling to the ground, he's actually my office mate. So I'm very proud to introduce him today. So please, yeah. By the way, he's a Ph.D. student at Saclay University and also Citè University.
Yes.
Yeah, I see many faces that are worked from there. He works on the largest scales of the universe, in particular on the cosmic microwave background radiation. I think we will know about this by the end of his talk. And on the distribution of galaxies over the whole universe. He's a member of the LiteBIRD collaboration. And which
LiteBIRD.
Oh my God, LiteBIRD. I'm so sorry. A typo.
Little bird.
LiteBIRD?
LiteBIRD.
LiteBIRD.
Yeah, still.
LiteBIRD. I'm sorry,
LiteBIRD.
I'm not native speaker. I'm from Chile. And
You used Oscar like you didn't live in the USA for like.
so this satellite was supposed to be launched in 2032, and the goal is measuring the effects of the primordial gravitational waves on the cosmic microwave background. And he hopes to still have a job for that year.
Yeah, we hope so.
So please,
All right.
Start introducing the
I
person.
will introduce my. Okay, so today I will tell you about the cosmic inflation, which is not economic inflation, but first, haha, I failed. I got you, right? It was just to capture your attention. Now, I'm a genius, I know, but it's not economic. It's not economic process. That's lucky because I am a PhD student, so I have no money and no power to discuss economics. But it is something way cooler. It is the expansion, accelerated expansion of the universe just a fraction of a second after the Big Bang. So it's technically not the Big Bang itself, but I will not like confuse you with many definitions. I will just show you how cool it is. Yeah, okay, you can stop pretending that it's cool. I will add some explosions so that you are happy. Wow, now, right? It's cool. Okay, I guess enough of that. We can start with the science. I guess we're kind of like all familiar with the concept of an accelerating, expanding universe at the beginning of time. But does anyone know why scientists have introduced it? I don't want an answer. It's just because it solves this problem. And just like anything in physics and in science, you have a problem, you find a theory that solves the problem, and then you study the consequences of the problem. That's the creator of Skyrim. Todd Howard. Yeah? And it just works. It's mirrored. And I mean, I'm not saying that like it's just because they wanted to make a really ugly TV series that nobody likes. And just saying that, wow, yeah, I just said that, yeah. And it's just that as science works, you find problems, you solve problems with a new theory, you test the consequences of the theory, and you study new science. Now, let's get actually to science. The universe is pretty empty if you are looking for a ride in the middle of nowhere. Yes, it's a Hitchhiker's Guide to the Galaxy reference. Obviously, I do physics, that has to be. But if we talk about radiation, it's not empty. It's actually full of radiation. And the fact that what we see here is the observable universe. It's the whole universe, and it's basically almost all at the same temperature, which is kind of like 3 Kelvin, which is kind of like minus 270 Celsius degrees. I don't know in Fahrenheit. It's not my problem. And the fact that it's all at the same temperature is surprising because that's thermal equilibrium, and that's something that happens for objects that are close. But does anyone know the distance between two opposite points of the observable universe? Not an answer. It's 92 billion light years, which is a lot, especially consider that the universe is estimated to be 14 billion years old, which is less than 92. And which means how did these two very far away points communicate? Well, to explain this, we have to go back to the 40s, when there were two main theories for the universe. The first one, the steady state model, which was supported by Albert Einstein, and basically who believed in a universe that always existed and remained the same even if it expanded. And the Big Bang model, which of course introduces a period of expansion after accelerated expansion after the creation, which start as a very small universe which expand itself, and this kind of explain the universe having just one temperature because it all started from the same point. So that's why those two very far away points are in thermal equilibrium, because once they were very close. So sorry, Albert Einstein, that's 1/0 for the expanding universe. And what's worse is that one of the fathers of the expanding universe theories was a priest, so very 1/0. And the cosmic microwave background radiation temperature is not the only problem. There is another problem which is slightly more complicated. So I will try to confuse you as much as possible so you think that I actually understand it, but it's not. It's the fact that the universe is very flat. Very flat, not in this sense, but in the sense that of the curvature of the universe itself, which it's better to visualize. If in a universe which is flat, if we take two objects traveling on parallel lines, they stay on parallel lines. If we study a universe with a positive curvature, they converge. If we study a universe with a negative curvature, they diverge. What's interesting about this, sorry for the cat, is that this curvature can be actually measured with the cosmic background radiation. And but to explain how, I have to admit it, I lied. This is not the observable universe. This is the fluctuations around the average temperature of the observable universe as seen by Planck, which is a satellite back in 2018. So basically, it means that these are zones with the orange zones are zones with a higher than average temperature. The blue zones are zones with a lower than average temperature. The average temperature was close to minus 270 Celsius degrees. And how can we measure the curvature? We can actually do that by studying triangles in the sky composed by a very cold patch, a cold patch, a warm patch, and us. And if we do that, we actually see that the universe is flat. Now, you may say, I don't care. The universe is flat. You're a nerd. You would be right. I am a nerd, but that's not the point. The point is that a curvature, since the universe is very old, any curvature at the beginning of the universe would have had the time to increase. So it means that if we see a very flat universe now, it means that at the beginning of time would have been super, ultra, mega, incredibly flat, which is too much of a coincidence. And to explain how the inflation solves also this problem is because if we think like of a curvature at the beginning of time, with inflation it is stretch and stretch and stretch and becomes more flat. Just like for us, seeing the curvature of the Earth, it seems flat to us right here because we are very small compared to the curvature of the Earth itself. I hope I didn't lose you. If I do, here it is something to win you back. Okay. Okay, I guess the attention span is back. We have introduced some of the problems that led to scientists to introduce inflation, which again is the theory of accelerated exponential expansion of the universe after the Big Bang, which means that the universe started as a very, very small universe and then became in less than a second very big, like from an atom to a solar system. And but what I'm trying to say is that as everything in modern physics, kind of everything in modern physics, every interaction in modern physics is described by particles, there has to be a particle explaining this expansion as well. I will show you now a very complicated table of all the particles that have been found, so you think that I'm smart. But what I want you to remember is that interaction equal particles, particles equal more particles, kind of, and that's it. Because obviously, as I said, inflation has to be produced by a field which has a particle associated and so on. The particle we are talking about here is the inflaton, very similar to the name inflation. Inflaton has a really large energy associated to it, which is basically released at the end of inflation to create more particles. That all the particles that populate our universe. And as every quantum objects, the quantum field of inflation is supposed to have quantum fluctuations, which we can kind of like visualize as oscillation of this microscopic quantum fluctuation of the field associated to this particle that made with a large energy that made the universe expand. But the point is that these were quantum fluctuations, which means very small. But inflation acted as by stretching these fluctuations to larger scales and leaving them imprinted in the history of the universe for the rest of time. After this, the universe is very hot. Very hot, like 10 to the 27 degrees, which is like this number, so a very big number. And it's filled with plasma. To explain what plasma is the fourth state of the matter, and that comes before gaseous. The annoying kid like to remember everyone at school. I was the annoying kid, of course. I guess a lot of physicists here as well. And we can imagine them as a flame, because if a flame is hot enough, it has electric charges inside, and at that point it can be considered plasma, like on the sun, for example. So that kind of state of the matter. Our primordial plasma had charged particles like electrons, protons, and photons, which are not charged. But charged objects on the macroscopic level in our everyday world behave by repelling each other if they have the same charge, or attracting each other if they have different charges, right? On a macroscopic level, they interact exchanging photons. Okay, we go back, and basically it's what photons are the particles describing the electromagnetic interaction of a quantum level, so a very, very small level. Now the universe continued to expand and to cool down after inflation, so after this very fast expansion, and for about 400,000 years, so a lot of time, charged particles continued to exchange photons until it reached 3000 kelvins, which is 3000 degrees. It's still a lot, but it's enough for the first atoms to be formed, hydrogen atoms, which meant that since they are electrically neutral, in a sense, they do not interact with photons anymore. And so we are in basically like 400,000 years in. We have hydrogens, we have the first atoms, we have photons that are moving freely. But the point is that this is happening everywhere in the universe. So basically, like, we have photons going in every direction, and they arrive to us as well. 13 billion years later, these photons arrive to us, and it's exactly this. Is the cosmic radiation that we see. But now, the cosmic background radiation seems to be like the incredible source of information and knowledge on our universe, and money for me, because that's what my PhD is about. So not that much money, honestly. But what I do specifically on this is study the correlation of 3 points on this radiation you remember the two points on this radiation could tell us some information about the curvature of the universe. 3 points, if we could actually be able to measure, will give us the ability to distinguish between different inflation models. Why? Because as I said before, the inflation at this fluctuation extended to larger scale, and that can actually be seen in the radiation, in this background radiation, which means that if different models have different kind of fluctuations, that can be seen in the cosmic background. Now, what I mean about a different inflation model is just a different way of this energy can be released and different type of fields, but and different way new particles are created. But the point is that it's not yet seen. The 3-point correlator is not a very strong observable. But nonetheless, if I will be still working in 2032 or possibly, because still not sure we are sending this satellite, but if we do, and I'm still alive, I will try to measure them with the LiteBIRD satellite, and which is another mission that is supposed to be launched in 2032 to measure the cosmic microwave background. So before thanking you, I would like just to make a very small summary before the questions, because I've seen there are too many experts in this room, so I've said a lot of maybe slightly incorrect stuff. First of all, we had problems. The universe was all at the same temperature. The universe was very flat. We introduced inflation as the exponential expansion of the universe after the Big Bang. This could actually solve some of the problems, because it started from the same point and expanded fast and stretched all these it made the universe more flat. Now, it has obviously consequences. It creates particles, plasma cools down, creates plasma becomes atoms and free photons. Free photons are free radiation. Radiation is freely arriving to us. This is the cosmic background. The cosmic background has fluctuations that are connected to the quantum fluctuation, as seen as being model dependent, and this could allow us to distinguish between models that describe how the universe behave like less than a second after the Big Bang. So very, very simple, very fast. I hope you understood. If you don't, feel free to ask any question.
Yeah. Wow, I see that Michele has very enthusiastic supporters.
Hooligans.
Do you have any questions for the speaker? Okay. Yes? Okay. This is just for the recording. So, yeah.
What is the difference between the LiteBIRD and Planck, and why do you expect that it will?
Okay, I did not talk about that. The reason is that it's a bit more complicated, but because I expected people to be less expert than all this side of the room. But and maybe somebody there. So basically, is because Planck did not see a part of the polarization of the cosmic background, because the cosmic background is polarized. Yeah. it's like the light has like two states, and one is just and the other is like very this is polarized. And there are two polarizations, and there is the E, and there is this polarization here, kind of. And the temperature, the E polarization, has been seen by Planck. LiteBIRD wants to measure the B mode polarization, which is not associated to scalar fluctuations, if you know what scalar is in the sense of the metric, but to tensor fluctuations, which are gravitational waves. So it's the B mode polarization in the cosmic background can be associated to generated by tensor fluctuations with our primordial gravitational waves. So seeing B modes will mean to like indirectly prove the existence of primordial gravitational waves that obviously are not it's not possible to see them with the modern interferometers. It's also my job in particular is still it's just hoping that we actually can measure the 3-point correlator even just for temperature and so on. But because obviously that's a measurement of non-Gaussianity, and the cosmic microwave background is very Gaussian, so it's like a guess. But the main goal is the B mode, is see that and say, okay, there is primordial gravitational waves. And for the non-expert there,
Michele, what about multi-field inflation with exotic kinetic terms?
I wrote that question. She has no idea what she's saying. Okay, if you have any other questions. You expect the angle between a kind of like a cold one and a warm one to be like 1 degree in a sense, and any deviation from that means that it's either positively curved or negatively curved, but it's very, very close to that. So it's saying that it's very close to the it's model. It's like when you write down the metric, there is like this term which explains curvature, and if it's there, it can be negatively curved or positively curved, and what we see with this 1 degree, it means that it's exactly zero curvature, so it's flat. Okay, exactly, kind of.
Like it's the closer warm point to a cold one.
Kind of, yes.
We have a question over there? Yeah.
So I forgot what you are doing.
Basically, I'm stealing money from the French government. No, no.
If this is being recorded.
No, I'm joking. I'm working. They can prove I'm working. I'm always in the office working. No, what I do is the 3-point correlator. Like you have a spherical distribution which is looking at the CMB everywhere, and I basically compute the Fourier transform of the 3-point correlator, which is the bispectrum. And the bispectrum can be, I will get more technical, but you'll tell me when to stop. The obviously, like just as the power spectrum, you have like the primordial bispectrum, and then you evolve it and you get the CMB bispectrum. For the bispectrum, you can do that the same as well, and it's very model dependent in the sense that there are some specific shapes that we expect to see, because this is a triangle, it's not more aligned as the bispectrum, so it can be really squeezed or equilateral and so on. We can like say just already by not seeing that, it means that, for example, it's very adiabatic, because any other isocurvature mode, we haven't seen any isocurvature mode, so it means that it's very adiabatic and there is no non-Gaussianity isocurvature. And also, for example, exotic models with exotic terms of kinetic terms could actually produce more non-Gaussianity, so that's also like kind of like neglected. So it's like you can actually rule out model at the moment. If we could actually see that, we will have a really strong way to decide which one is the correct one. Obviously, we are not able to do that yet, because our non-Gaussianity is basically 1 plus or minus 10 at the moment, so no information because our error is too big.
Okay, so I think it was getting a bit too technical. If somebody has a question that is more general audience.
What's my favorite color? Blue. No.
You had a question? Yeah.
It's not exactly general audience. Do you have any comments on the claim detection on the galaxy, or like the 4 points function?
The 4-point function?
Yes.
Well,
there were like
three spectrum.
Yeah, there were some claim detection on the spectrum in galaxies, so in late time universe.
Well, I'm talking about I'm talking about the primordial one, because obviously the equation of Einstein are non-linear, so we will have like late time non-Gaussianity for sure. For example, in large scale structure, they all study the bispectrum, but they just study the non-linear evolution of the power spectrum, which will give you a bispectrum and the trispectrum and so on. So you will actually have a sign, like a notable signal to noise ratio. The point is that that's not primordial. It's not coming from inflationary terms. It's just due to the evolution of the universe, for example, in large scale structure and distribution of the galaxies.
So in this paper, they were claiming that it was a early universe because it was on the. It couldn't be caused by a late time.
Well, technically, they should be always less important, the bispectrum, trispectrum, and so on. So it seems a bit like
We'll come with more precise
okay,
reference.
but I mean, there was also a paper claiming they saw that between in cross correlation terms between the CMB and large scale structure, they saw the trispectrum. So it's possible. I'm not sure.
Thanks.
Okay.
Welcome.
I see a question in the back. Yes.
Why do you call it 3 points, not 1, 2, 4, 5?
Well, because technically is the same that is as in statistics. We all know what a Gaussian is. A Gaussian has an average, a variance, and then there is the K and S, which are called the skewnesses and the kurtosis, are 0 for a Gaussian, and so on. But every statistical distribution has this momentum distribution as well. And bispectrum is basically the first non-Gaussian term of this 2D distribution because it's a sphere. Like you look in the sky and you see the CMB coming from everywhere. So it's basically a 2D distribution. And as a probability distribution, it has moments, and the 2-point correlator is the most valuable source of information at the moment. But it's Gaussian. It doesn't deviate from a Gaussian. If we actually see the bispectrum, that will be the first momentum, non-Gaussian momentum. Obviously, if you linearize the theory, every momentum bispectrum and so on, they are all 0 because it's a linear theory. It's Gaussian. If the moment we go to a first non-linearity, we are introducing non-Gaussianity. How strong it is at the moment is very weak.
I have a question.
Okay.
So a few years ago, yeah, it's hot, right? We can try to turn it on later on. So we discovered a few years ago this particle that actually gives the mass to other particles.
Higgs.
Right?
Yeah.
So, but do you have any idea what the properties of this inflaton can be,
Yeah.
and if it's possible to ever discover it?
Yeah, I mean, it's a scalar field. There are some models that are called the Higgs inflations, which basically say that this scalar field should be the Higgs field itself. I'm not sure if it was ruled out. I think that critical Higgs inflation is already ruled out. So there is some. It's a strong assumption.
Yes.
But seeing that, I think it's difficult because I don't think you can create it in a lab, like at the CERN, because it's like the scale energy you need would be the level of the universe scale energy.
Oh, we need to create another universe.
So I don't think, but so I'm not sure how Higgs inflation works for that reason, because Higgs has been seen, but for the usual one, it's not. Especially, and you don't see people in the beyond standard model try to work out ways to produce inflatons. So it's like a very behind, and it's already indicated because it's in the. It should be like ended inflation, so it's at the bottom of this rolling down potential. So I guess there is no way to recreate it. But I'm not a particle physicist. Yeah, we have some here in the house. If you want to say something.
I know this audience is very well educated. I hope like everybody is getting all the questions.
I mean,
do you have any more questions? Yes. Oh wow. Yes. Yeah.
Every mission have like an acronym usually. So what means LiteBIRD?
LiteBIRD, it means light, in the sense that it's very underfunded. I think something like that. I think it was like actually a joke against the Japanese financing program that was saying like, okay, we are very light on the money. Bird, that's a good question. I guess it's the usual, like people liking to make fun acronyms. Let's discover that. Yeah, for sure. Be more inflation, blah blah blah. LiteBIRD. Light, satellite for study of B mode polarization and inflation for cosmic background radiation. They really chose just the words they wanted and capitalized them. So yeah, we wanted to write bird, so let's choose B, I from inflation, R from radiation, D from detection, and the rest is.
Who cares about the rest?
Yeah. The rest is. So yeah, LiteBIRD.
And maybe one last question, yes?
My question was before there was the CMB measurements by Big Bang. What was the things that would distinguish the steady state model and the...
I mean, there was other measurement with WMAP.
Okay,
Yeah, there was previous experiments, and I think that the temperature of the CMB was measured like way before with like by mistake, because they had like this noise that was not able to get rid of at this temperature, like 4 Kelvin, something like that, and at the in the microwave regime. So they said, okay. I think it was even measured before by mistake by measuring the temperature of a star, and they had like this something off. They said, yeah, it must be something wrong. So it was actually already visible. They were already, after just the first, were already some strong signs of at least the monopole, which is this average temperature, which is 3 Kelvin, which is already enough to prove the existence of the radiation. Then the fluctuations are seen way lower Kelvins, 10 to the minus 3 and 10 to the minus 5 and so.
Okay, if there are more questions, we can probably keep them for the break in between the talks. So let's thank Michele again.
Thank you.